Okay, so that was a very simple approach. We've taken a loop that is naturally parallel. We've decorated it with OpenACC to express that there is parallelism there, and we've achieved a speedup. I haven't shown any results here because depending on the size of your problem, you'll get differing results. But that was a very straightforward approach there. Now, what if we wanted to do a more real-world example? What if we want to do something more complex than a single naturally parallel loop? And so I'm going to use a code that you've probably seen before. Again, maybe you haven't. It's called a Jacobi iteration. So here what I'm going to do is I'm going to iteratively converge on some value, whether it be temperature, pressure, whatever's of interest to you. I'm going to iteratively converge upon that by looking at my neighbor's values. So if you look here in this square, this middle dot can calculate its new value based off of the average of the 4 neighboring dots. So that's what the math says here. So very commonly used algorithm, very useful algorithm. So let's look at how it's implemented. We have here a convergence loop. It's going to iterate until one of two things happens. Either our error value is within some max that we have set up, and the error value is simply a difference between my new value and my old value. And if everybody's new value and old value is within some level of tolerance, you decide, okay, that's close enough. The other thing is you could iterate to some maximum number of iterations. That way we don't continue on forever and ever if we're not getting convergence. And in the case of all the data I'll show you, everything has been set up to always iterate 1,000 times. Next, we're going to iterate across all of the matrix elements, and we're going to calculate my new value based off of my neighbor's current values. I'm then going to calculate what the current maximum error is. So every single iteration of the loop is going to calculate what the error is, and if the error is larger than the previous max, it will update that. And then lastly, I swap the input and output arrays. Now, some of you might be wondering why I need 2 loops. Why don't I just update A directly in here? Well, if you watch closely, we'll have a dependence as we iterate, because when I calculate myself, I need to know what my neighbor's current value is. And if he has already updated itself, it's going to constantly propagate, and so we're going to get incorrect results. That also introduces a dependence that makes it non-parallelizable, because what I calculate is based off of what my neighbor calculated. And so if the previous loop iteration is a dependency, then this is not safe to parallelize. So what we've done is we split these in 2. That way, not only do we get the correct answer, but each iteration of this loop can be done in parallel, and each iteration of this loop can be done in parallel. So just as before, we're going to use OpenMP first to do this. And I've said here, parallelize this loop across CPU threads using OpenMP, and parallelize this loop. So now if you've not done OpenMP before, or parallel programming in general, let me explain that the shared scope is simply saying every single thread is going to use the same copy of A and A new. And that's safe because for IJ is only writing to its own element, so I don't have to worry about someone else stomping on my space. The other thing here is, if you're not familiar with what reduction is, if you think there are m times m iterations to this loop, and every single one of them is going to calculate a value for error. So I have m times m errors, and I want to get down to just 1. And that 1 is the maximum of them. So I'm saying I'm going to reduce from m times n values for error. I'm going to reduce it down to 1 using the maximum iterator, or the maximum operator. And that's very important, because if we run this in parallel, because this is floating point math, and that means the order of operations matters, we want to make sure that however many threads we run on, we get the same result at the end. So you tell the compiler, this is a reduction. That's not necessary down here because we're just doing data movement. Okay, so that's the OpenMP code. Here's the OpenACC code. Notice I don't need to give a shared scope anymore. That's just the default with OpenACC. I do still need to say it's a reduction, but all I've done is say, please parallelize this loop. Do it on the GPU, and also please parallelize this loop on the GPU. And what should happen is we should get 2 GPU kernels out of this. And if we look at the compiler output, we do. At line 56, we get an accelerator kernel, and at line 68, we also do. All of this other stuff we'll learn to read later, but notice we're copying data in, we're copying data out. This is kind of telling you how the loop gets decomposed. All of that we'll go through a little later, but it gives you a lot of information about what the compiler is doing to your code. And now if we run it, you can see here's the serial code, about 1.5 minutes. 2 threads is 52 seconds. 3 threads is about 40 seconds. Notice this is not a linear speedup. This is a very, very memory-bound code. And it's really by adding more threads, or even adding faster threads, we're not going to get an additional speedup because it's very much memory-bound. Oops. And so if we look here, we eventually get down to about 38 seconds. And now, congratulations, you have successfully slowed down your code with OpenACC. Now, I don't want anybody to leave right now because I don't want you thinking that's what happens with OpenACC, that you're going to make your code slower. In fact, I want you to learn when this does happen to you, how to approach it and how to find out what happened. And it turns out it's very simple to fix this code. So let's see if we can figure out what happened. And to do that, I'm going to use that environment variable that I told you about, the PGI ACC time. And so here is our runtime profile. You notice there are 2 accelerator kernels that we expected. It actually is also a reduction kernel. On the left and in green is the time that we call compute time. And so, 2.5 seconds, or a little over 5 seconds in compute time. This is when the GPU is actually busy doing meaningful work. In red and on the right is what we call data time. Or data transfer time, 23, 24, 28 seconds, 25 seconds. Clearly, whatever data transfer time is, that is what is bounding our performance. So here, 75 seconds in data movement, 5 seconds in computation. So what's happening is, we have here a very simple CPU and GPU node. In this case, I'm only going to show one of each. You could have multiple of each if that's what your system looks like. CPU has its memory, GPU has its memory. And of course, they're connected together by the PCI Express bus. Now, the gray bars are not to scale, but they are meant to kind of show you that the CPU's access to its memory is very fast. GPU's access to its memory, it's even faster. But the PCI Express bus is comparably much, much slower than either of those. So what happens when we offload our work is, first, for every parallel operation, we're going to copy the data that we need from the CPU to the GPU. We'll compute on it one time, and we'll return the data back. So that's what we're doing when we just insert these parallel directives. And so if we do a lot of computation, there's going to be a lot of movement across this little pipe. So what we need to think about is, how can we separate these two concerns? How can we think about data movement and computation separately? And it would look something like this, where we'll move the data from the host to the device when we need it. We'll compute on it as much as possible. In this case, in my example, I'm going to compute on it 3 times. And then when all is said and done, then I return back the results that I need. So I've completely separated the concerns. I'm only going to move data when I absolutely need it, and I'm going to compute on it as much as possible. If you've done any GPU programming at all, you're familiar with this concept, right? We only want to move the data as little as possible. So how would we do that with OpenACC? Well, first, how does this apply to our existing example? So here is our iteration loop. When we come into the iteration loop, or the convergence loop rather, we have A and A new, and those living on the CPU. And in OpenACC language, the CPU is called the host. We're going to copy it to the device right here. It's now going to be resident on the accelerator, or in OpenACC words, it's the device. We'll work on it. This is our main loop here. And then we're going to copy the data back. And of course, we have our update loop as well, so we're going to have to copy the data back over there, work on it, copy it back. So we have 4 copies per loop iteration, and there's 1,000 loop iterations, so we have 4,000 data copies. And actually, if you looked very closely at the data I showed you a minute ago from the compiler runtime, you would see there were 4 data transfers, each happened 1,000 times. And I highlighted that in yellow if you want to look back at it later when these slides are available. So we have 4,000 copies. Now, how can we improve this? Does anybody have any suggestions of ways to improve this? In the back. Right, so share the data between the 2 kernels is essentially what you're saying. And so we could eliminate these copies here because we recognize the fact that this kernel and the second kernel use the same data. Good first start. What's the next step? What else can we do? Yes? Allocate A new on the GPU and recognize the fact that we don't need to copy that back and forth at all. So it's a new is a temporary. Any further ideas? There's one more thing. Right, so don't copy the data until we finally need it at the end. Run until we've reached the tolerance. That's exactly what we need to do. So first thing we'll do is we'll combine the fact that these kernels use the same data. We'll also recognize the fact that we don't need the data till the very end, and we'll also acknowledge the fact that a new is a temporary. So all three of those approaches are what we can represent at OpenACC. So how do we do it? We use this data region. And so the data region, it simply defines a region of code where your data remains resident on the GPU for the entire extent of that region. So here I have an ACC data, and I have two parallel loops. And so the data gets copied in at the beginning, copied out at the end, but remains there throughout. So right there, we've done enough to share the data between the two kernels. But we can give a lot more information than that. We can use data clauses. So the first data clause here is the copy, and that's a two-way copy. So if I need I need the initial values of A, and I need the final values of A, that's a two-directional copy, so I'll copy it in and copy it out at the end. The next two we won't actually use in this example are copy in and copy out, so there's a one-directional. I need the input value, but I don't care what happens to the array, or I need the output value, but I don't care about the initial. Create is what we'll do with a new. So create says this is a temporary. I don't care about the initial conditions. I don't care about the ending conditions. Just create it out on the device. Present is useful if you happen to nest multiple data regions. What you'll say with present is, at this high-level routine, I've already taken care of creating it or copying it. And at this low-level data region, I can just say it's already present and don't do anything else. And it turns out the present can be combined with the others and say present or copy in. So the first time you reach this clause, copy it in, copy the array in. But every time after that, it's already going to be present. So just reuse the same data, or present or copy out, or present or create. And the last one that I'm only going to mention we won't actually use in this example, you'll use it in the afternoon session if you come back, is device pointer. And that says, I've allocated this memory already using some other mechanism, CUDA-malloc, Kubla's create array, or anything like that, and just provide that to the device. So that's for interoperability. So now what we can do is we can tell the compiler not only to share this data, but when to copy it. Now, the last thing I need to tell you about these clauses is if you're using Fortran, you're probably already in good shape. Because if you're copying the entire array, Fortran is self-describing, and it will copy the entire array for you. However, if you're in C, or if any of your runtime information any of your sizes are determined at runtime rather than at compile time, you may need to give additional information, and that's called array shaping. So if the compiler can't recognize the size of your array or the shape of your array at compile time, it's going to abort. It's going to give up and give you a message saying, I need more information. And the way you give that additional information is with this sort of syntax here, where you say a bracket 0, 0 is my starting point, colon size, copy size elements. Okay, so 0 and size elements. Or you can give partial arrays if you don't need the entire thing. So it turns out if you do want the entire thing, you can actually leave off that initial 0 just as a convenience. But here I'm saying start at s over 4 and copy 3 times s over 4 elements. So you can specify exactly what you want to copy. In Fortran, it's a subtle difference. First off, it's parentheses rather than brackets, as you'd expect. But the subtle difference is it's the starting point and the ending point. So 1 through end. They're functionally equivalent, but that's just a small difference here. Or again, s over 4 through 3 times s over 4. So that's how you provide the information necessary about what your arrays look like. And there's a little more good news here, is that you don't necessarily need a data region. You can actually use these clauses on parallel and kernels as well. So if you have an outside data region, you can specify in the parallel region, it's already present, for example, or present or copy in. So you can use these same clauses on data, on parallel, or kernels. And that's just kind of a convenience for you. So let's see how this applies to our Jacobi example. So here, I've created a data region outside of the while loop. So anything inside this next while loop is going to share that same data region. I'm going to copy the input value of A, I'm going to copy the output value of A, and I'm going to make A new into a temporary. So now both of these will share the data. That was the suggestion back here. The suggestion over here was the fact that A new is a temporary, and the other suggestion in the back was not copying data until we're done. So we've done all three of those here just by adding this pragma at the top. Now, you can create a data region that's not followed by a loop. If you want to do that, you simply do a curly brace to mark the beginning and end of your data region. But here, because a while loop is inherently a block of code, we can just say pragma ACC data, and for the entire extent of this while loop, we will remain in that same data region. And running this, what we see from our setting our environment variable, now we've done one single copy in, one single copy out. Each of them takes about 1/4 of a second. So we've gone down from 4,000 copies to 2. And of course, we get the speed up that we would expect. So now we're about 7.5 times faster than the fastest CPU code, or about 18 times faster than what we started off with, which was the serial code. So all of this came from recognizing the fact that we didn't first give up and say, oh, OpenACC slower, I'm done. But we recognize the fact that we need to think about data locality and how to manage our data. And I really do encourage you to progress through your code exactly how we've done this. Start off by identifying where there's parallelism in your code and use either parallel or kernels to express that parallelism. Do that throughout your code. Make sure you're getting the right answer. That, of course, is critical. Make sure that this doesn't change your answer. If it does, that means maybe these loops weren't actually safe to parallelize, and I need to figure out why. So maybe there's a dependency there. Once you're getting the right answer, then look at adding the data regions to reduce and optimize away your data movement. What I've found is if you do it in the opposite direction, it gets very frustrating because you'll set up a data region, and then you'll have to move the data region and change what you're copying in and copying out, and you'll have to move it again. So just go ahead and express the parallelism, get it running correctly. 9 times out of 10, I've found that at that point, your code is running slower. Then go back and optimize away the data movement, and that's when you start really getting the right results. So there is definitely work that needs to be done with OpenACC. As I said, it's not automatic for you, but by expressing the parallelism this way, I think you'll get nice results. Now, I'm not going to claim this is the absolute fastest that you can do. In fact, if you happen to know more about your hardware and know more about the OpenACC standard, you can actually give additional information. So if I know exactly which hardware I want to run on, I may want to tell it how to decompose my loops to that hardware. And so OpenACC provides the gang, worker, and vector clauses, and those will be gone over this afternoon in the 2:30 session to say how I decompose my loops. Also, if you want to profile your code, you might find that there's some bottlenecks that I wasn't expecting, that perhaps if I move some of these loops around, I might get better results. And so you can sometimes get even better performance just by looking at where these bottlenecks occur and seeing if you can express the parallelism at a different level. Frequently, what you want to do is get it at as high a level as possible. All of this is, again, in the 2:30 session for OpenACC. Now, that's all well and good. You're computing well in the GPU. You're getting fast results. Eventually, you have to get the data back. Eventually, you have to write it to disk. Maybe you're generating a weather simulation. You want to write out a movie file of what's happening. Maybe you're on a parallel machine with many nodes, and you need to use MPI to communicate between them. Eventually, the data has to come back from the GPU, which means you can't just completely eliminate the PCI Express bus. So here's an example. I'm going to use standard MPI to start. And what I mean by standard MPI is it expects CPU memory. So you're going to have to copy the data from the GPU to the CPU in order to use it. So that's all represented in this neighbor exchange routine. I've kind of abstracted that away. If you're not familiar with MPI, it's just a way to move data between nodes. So here, array A for this high-level example resides in GPU memory. I have a routine somewhere in the middle that requires the same data, but it needs it in CPU memory because we're using MPI. But unfortunately, the data doesn't get back to the CPU until this very bottom. Now, we don't want to break this up into 2 different data regions because then we're going to introduce additional bottlenecks. So let's say if there's 10 different arrays here. If we break this into 2 data regions, all of those arrays are going to have to be copied back and forth at the beginning and the end. What we want to do is remain in this data region as long as possible so that the data remains resident. So we're going to use something called update. The update directive is just a way to refresh the data from one direction or the other. And so what you'll say is, I'm doing something on the GPU here in green. I'll then say ACC update host says copy A from the GPU to the CPU. And of course, if you only want part of the array, you can use the array shaping I mentioned earlier. I'm going to do something on the CPU as well, and then refresh the data back again. Copy A from update array on the device, update on the host. So that's how you would do this. So here I've taken that same example, and I've simply added the update host of A and update device of A. And in the middle, I'm using A on the CPU. So this is a pretty straightforward approach. Here I'm kind of saying it's going to be done with MPI, but it could just as easily be done with any of your I/O libraries. If you're just doing a periodic checkpoint of where you are in case your job ends, or if you're generating a movie file or something like that, you can use that at any time to say update the host and then keep going. And if you were to make this asynchronous, you could copy the data back and then keep working on something else as well. So there's a lot of different ways you can use the update. Now, what if I want to use an MPI that understands GPUs? So there's a few different talks this week about GPU-aware MPI, and this is also applicable if you're using, say, the coples library or any of the GPU-aware math libraries. You want to pass in the device copy of your data because that's what it's expecting. And we're going to use something called the host data directive to do that. So it's not intuitive, right? We're using the opposite terminology here. Host data says everything inside of this region is the host copy, the CPU copy of my arrays, unless I specify otherwise. And I specify otherwise with the use device here. So ACC host data, use device of A, and now MPI send receive, which is just a standard MPI call, is going to get the GPU copy of A. Or down here, pragma host data use device of A, call coples dgem on A. So if your library expects GPU data, you can use this pragma to expose that to the library. So this is some of the interoperability that's available to you. And here's the same example here where I'm now saying pass the device GPU copy of A. Now my MPI aware or GPU aware MPI is going to use that, and then it ends at this point here. So, okay, so we're actually progressing very quickly here, so there should be plenty of time here for additional questions. Some tips and tricks for you as you begin using OpenACC. First, if you're a C programmer, the restrict keyword is very important when you're doing any form of parallel programming. This could be OpenMP, this could be OpenACC, this could be just trying to take advantage of the vector instructions on your CPU. In Fortran, if you allocate two arrays, A and B, they will always be two distinct bits of memory. They're never going to overlap. They're always distinct. C, we only deal with pointers, right? And so the compiler doesn't know that you can't do something fancy. I mean, C is a pointer-driven language that allows you to do many, many things with that, sometimes at your own peril. And so it allocates A and you allocate B, and chances are, 99+% of the time, these are two distinct bits of memory. The compiler doesn't know that. The compiler doesn't know that they don't overlap in some way, that B may be aliased to some member of the A array. And so it has to assume that that's the case, which means it's not safe to parallelize, because if you're storing into B, that's really changing A. So what you have to do is tell the compiler, these are two completely separate pieces of memory, and you use the restrict keyword. So this is a promise I make to the compiler that I'm not aliasing. Now, if you break that promise, all bets are off. The compiler may do additional optimizations that turns out weren't safe. So all of you C programmers, this is how you use it if you've never used it before. I'm saying pointer A is not aliased to anything else, so it's a float star restrict pointer. And so for the lifetime of pointer, it will never be aliased to something else. So the way you'll recognize when this is the problem, if you have a C code and you put OpenACC in it, and it says Data dependency, I'm not parallelizing this loop. If you see that data dependency and you're staring at your code and you can't figure out why there's a data dependency, where there's a data dependency, almost certainly it means the compiler doesn't recognize this because it has to be cautious. And so adding this restrict keyword is the way to get it to parallelize. In general, nested loops are a great source of parallelism. So very few codes are blessed with single flat loops that have a million iterations. Some of them do, they exist. But most of the time what you're looking at is you'll have these inner loops that are some small number of iterations. One of the codes I was working on recently, the innermost loop dimension was 4. Well, there's clearly not much parallelism there. But if you start adding the nested levels of parallelism and multiply those together, you get many, many more levels of iteration. So if it's not enough parallelism to warrant a port to CUDA, there's not enough parallelism to warrant using OpenACC. You need thousands, hundreds of thousands, millions of independent loop iterations. And it's important that those iterations are completely independent of each other. And again, if you're a C programmer, using the restrict keyword tells the compiler, it helps the compiler identify that that's the case. The compiler needs to be able to figure out at compile time the sizes of your arrays. And so if the compiler is complaining, I don't know what the shape of this array is, use the array shaping clauses that I showed you in order to do that. In the current OpenACC spec, you cannot make function calls within a parallel region. What you'll have to do is inline them. So the PGI compiler has this minline flag that you could say inline all of these routines. Or the Cray compiler uses what they call their program library, which will generate a library that will then link in and use that. Now, this is something that changes in OpenACC 2. And again, that's not implemented anywhere yet, but it's in public comment period right now, where you can specify, here is a subroutine that I am going to call at some point on the GPU, generate a GPU version of this, and it will use that to build your code. So that's something that does definitely improve in the 2.0 specification. And that allows you to put your OpenACC directives at an even higher level in your code. All of the different profiling tools that you're familiar with are available to you. So if you're familiar with Visual Profiler, if you're familiar with NVProf, if you're familiar with the command line profiler, all of those tools will work with OpenACC. Also, the 3 compilers have their own environment variables you can set. You've seen this one. Cray ACC Debug is a very nice one that gives, depending on the verbosity level, information about what's being done, about how your code is decomposed, how your loops get broken down into the hardware. Or this is the CAPS one. And this, if you set the log level to info, you get a lot of data. And so you'll probably want to pipe that to a file so you can look at it. Pointer arithmetic. The trick with pointer arithmetic is you can do some very clever things. And sometimes those clever things can do some very nice optimizations to your code. But unfortunately, that makes it difficult for the compiler to understand what you intended to do. The compiler has to understand your intent in order to generate a good parallel code. And so using too much pointer arithmetic can confuse any compiler. And so I encourage you, use array subscripts rather than saying a pointer and the offset. And that will give the compiler your intent, and it will be able to generate better code. In addition to that, if you have multi-dimensional arrays, in C, a lot of people have one array of pointers and then allocate every single row into with its own allocate statement. Well, that will result in, if you have n rows, n copies across the PCI Express bus. If instead you have one large contiguous array and you calculate from that, you can have one bulk transfer to the device. Now, this is much easier, I acknowledge, in Fortran than in C, but that will be one bulk transfer will always do better than n smaller transfers. Always use the data regions to represent when to move data around. So those of you who have already done GPU programming are familiar with the fact that we want to eliminate the PCI Express copies as much as possible. There is a handy macro that's given in the specification. It's _OpenACC. And if you use this, you can selectively compile parts of your code. So one way I've done this is I'll have a big loop nest that I have OpenMP directives on, that I'll use that unless I'm building OpenACC, so I'll use this to specify at compile time whether I'm using OpenMP or OpenACC. So that's a nice handy way. I've also used it before where if I want to do something slightly differently in the CPU code versus the GPU code, you can use that to again flip on a certain portion of your code using OpenACC. So all of this is done automatically. It's defined in the specification. What that actually sets for you is the date of the spec ratification, so you can also determine whether it's OpenACC 1.0 compiler or 2.0 compiler. At this point, I'm going to go ahead and open the room up to questions.